So today we're gonna start with the new topic, that is your, of course, the unit 11, which is the p block element. In that same way, if I'm going ahead, we had done in p block also we had done before that the s block element, and that is the important one, of course, and has been completed, where we had discussed about the questions as well. If you had not visited that, you can just go ahead. Before starting with the same, it's a huge request to all the viewers to please go ahead with like, share and subscribe, so that many and maximum people can get the information at once, and you can also enjoy the video as well. So here in the same way, this is the chemistry for class 11th to class, and that is your 22th class of the session. In this we'll discuss about unit 11, that is the B block element, and unit 10, the S block element we had covered up. In P block element here, the variation in properties of a p block element due to the influence of a d and f elements, a d and f electron in the inner core of the heavier element, that makes the chemistry interesting. In the same way, for the p block element, in p block element, the last electron enters the outermost p orbital, as we know that the number of p orbital in 3 is 3, and therefore the maximum number of electron that can be accommodated in a set of p orbital is 6. Consequently, there are 6 groups of p block element in the periodic table, that is numbering from 13 to 18, which is your boron, carbon, nitrogen, oxygen, fluorine and helium. Head on the groups. The valencies of electronic configuration in S is ns2 and p1 to 6. So I just write for you all the valence shell electron configuration. Valence shell electronic configuration is ns2 np from 1 to 6, except helium. The inner core of the electronic configuration may however differ from the difference in the inner core of element and ionic radii as well, atomic and your ionic radii, that is ionic core of element as well, that greatly influence their physical properties such as atomic number, atomic and ionic radii, ionization enthalpy, etc., as well as the chemical properties. Consequently, lots of variations in properties and elements in their group of p block is observed. The maximum oxidation state shown by a p block element is equals to the total number of valence electron, that is the sum of s and p electron, and clearly the number of possible oxidation state increases towards the right of the periodic table. In addition to this so-called group oxidation state, where p block element here, that is in the same way, we just like lots of variations in properties, and consequently a lot of variation of properties of elements in the group of p block element is observed, where the maximum oxidation state that has been shown by p block element is equals to the total number of valence electron, that is the sum of s and p electron. Clearly, the number of possible oxidation state increases towards the right of the periodic table. In addition to this so-called group oxidation state, PL block element may shows other oxidation state which normally but not necessarily differ from the total number of valence electron by unit of 2. The important oxidation state exhibited by p block element in boron, carbon, nitrogen families, and the group oxidation state is most stable state for the lighter element in the group. However, the oxidation state 2 unit less than the group oxidation state become progressively more strongly and the heavier element in each group. The occurrence of the oxidation 2 unit less than the oxidation state that are some attributed the inner pure effect. So what is inner pure effect? That we will be discussing here. So before starting discussing about inner pure effect, I just make you write about that so that you will be able to understand what it totally stands for. Inner pure effect, that is attributed to the inner pure effect. So in terms of inner pure effect, we have here, so the oxidation state two unit less than the oxidation group. State becomes progressively more stable for the heavier elements. Elements in each group. The occurrence of oxidation state two unit less than the group. Oxidation state are sometimes attributed to the inner pure effect. Now coming towards detail about the p block element that we have discussed here, which we will discuss about the table that is being related to it and which has been the important as well. So here we go. We'll discuss about the group electronic configuration and oxidation state of p block element. So let's go for the same. So first we'll discuss about the group 13, 14, 15, 16, 17 and 18. Okay. The group we'll talk first about general electronic configuration. Then after that we'll discuss the first member of the group. We'll discuss the group oxidation state. Another is your other oxidation states. Okay. Now we'll go for detail about it. This is your general electronic configuration. An oxidation state of p block element. Now we go for it. For general electronic configuration that we have, general electronic configuration for N13 group, NS2 and P1. For 14th group we have NS2 and P2. For 13th group, the first member of the group is boron. The group oxidation state is +3 and the other oxidation state is +1. For group 14, the electronic configuration is NS2 and P2. The first element is carbon. Group oxidation state is 4 and other oxidation state is +2 -4. Now coming towards group 15, that the general electronic configuration for group 15, we have NS2 and P3. Now we go for a group 15, that is the first member of the group 15 we have here is, that is nitrogen. The group oxidation state is +5 and other oxidation state is +3 -3. General electronic configuration for group 16, we have NS2 and P4. The first member of this group is oxygen. Group oxidation state is your +6 and the other oxidation state is +4 +2 -2. Coming towards group 17 here, that is your group 17, we have your general electronic configuration is NS2 and P5. The first number element is your fluorine, +6 7 plus 5 plus 3 plus 1 minus 1. Now coming towards your group 18, the general electronic configuration, we have NS2, NP6 and 1s2 for helium. The first member is your helium. That is the electronic configuration we have for that is 8, and here we have our little plus 6 plus 4 plus 2. Okay, so this is the general electronic configuration of oxidation state of p block element, and that is what you have to follow here as well. In the same way, with reference towards it, we'll go for further in the detail about this. So other than this, they are the relative the stabilities of these two oxidation states, group oxidation state of the unit less than the group oxidation state, that may vary from group to group and will be discussed in an appropriate place. It is interesting to note that the non-metal and the metalloids that we have exist only in the p group, a p block of the periodic table, and the non-metallic character of element that decreases down the group. In fact, the heaviest element in each p block group is the most metallic in nature. This change from the metallic to metallic character that brings diversity in the chemistry of these elements, that is depending on the group to which they belong. In general, the nonmetals that have heavier ionization enthalpy and higher electron negativities than the metals, hence in contrast to the metals which rarely form cation, non-metal that rarely form anion, and the compound formed by highly reactive non-metal with highly reactive metals are generally ionic because of large differences in their electronegativities. On the other hand, compounds formed between nonmetals themselves are largely covalent in character because of the small differences in their electronegativities. The changes of nonmetallic to metallic character that can be the best illustrated by the nature of oxide they form. Non-metal oxides are acidic or neutral, whereas metals oxides are basic in nature. The first member of the p block differs from the remaining members of their corresponding group in the two major respects. First, in the size and all other properties which depends on size. Thus, the lightest p block element that shows the same kind of differences as the lightest s block element, lithium and beryllium. The second important difference, which applies only to the p block element, arises from the effect of d orbital in the valence shell of heavier element starting from the third period onwards, and their lack in second period elements. The second period elements of p group starting from boron and restricted to the maximum covalence of 4 using 2s and 3 p2p's orbital. In contrast, the third period element of p group, which is the electronic configuration of 3s2 3pn, have the vacant 3d orbital lying between the 3p and the 4s level of energies. Using these d orbital of the third period element that expand the covalent above 4, the 4, while boron forms only Bf4 minus, aluminium gives AlF6 3 minus ion. The presence of these d block element influences the chemistry of the heavier element in the number of the ways. The combined effect of the size and the availability of the d orbital considerably influence the ability of these elements to form pi bonds, and the first member of the group that differs from the heavier members of the ability to form p pi multiple bonds or to itself. For example, carbon second bond with carbon and carbon triple bond, like carbon second bond with carbon double bond and triple bond with carbon, or nitrogen, triple bond with nitrogen to the other second row element here. And the same way, example, carbon double bond oxygen, carbon double bond nitrogen, carbon triple bond nitrogen, nitrogen double bond oxygen. This type of pi bonding is not particularly strong for the heavier p block element. The heavier element to do form a pi bond, but that involves d limit orbitals, d pi and p pi or d pi or d pi. As the d orbitals are the higher energies of the p orbital, they contribute less to overall the stabilities of molecule than does p pi bonding to the second row element. And however, the coordination number in a species of heavier element may be higher than for the first element in the same oxidation state. For example, in +5 oxidation state, both nitrogen and potassium form oxo anions, NO3, three coordinations of pi bond involving one nitrogen pi orbital and a PO3 minus 4, that is 4 coordination involving the S and P orbital contributing the pi orbital. And to this unit we will be discussing the chemistry of the group 13 and 14 elements of the periodic table. So here we're going to end up with. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in the comment box. Please like, share and subscribe so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Unit 10 we had completed the S block element. Unit 11 we had started the P block element. So stay tuned with us and thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in the comment box. Thank you.